So today we're going to start with lecture notes 2, where we're going to be looking at the equations of planes in 3D space. Really, the only difference between this course and your previous calculus courses is in your previous calculus courses you were dealing in 2D, and in this course we deal in 3D. So as a result, it really helps in this course if you can visualize in your mind what's going on in 3D. Not all of us are really good at that, and so for some of us we have to try a little bit harder than for others. But try to get into the habit of visualizing in your mind what's going on. If you can sketch well, that always helps too. I'm not a great drawer, so I tend to just try to visualize in my mind. And in this lecture where we start talking about planes in 3D space, it starts to become important to be able to visualize. It just helps you understand what's going on. So if I asked you, if we talk about 3D space, a 3D coordinate system, if I identify two particular points in 3D space, what will that give us? So if I got 3D space here, and I don't know, I got a point here, some point in space, and I got another point over here in space, what will that define? Well, that will define a line, right? I can imagine a line passing through those 2 points, and there is only one line that passes through those 2 points. So if I have two points like that in 3D space, they define a line. Now I can also talk about a plane, okay? And a plane is obviously a three-dimensional surface, a flat three-dimensional surface. So I could also talk about a plane that contains those 2 points. So I could maybe draw that plane like this. Okay, and that line would be in that plane, and those 2 points would be in that plane. Now here's the question. Is that the only plane in 3D space that contains those 2 points and that line? Anybody want to guess? Yes or no? Is this the only plane in 3D space that contains those 2 points? No, the answer is no, right? I could draw another plane, maybe looking like this. Which also holds those 2 points and that line. Okay, so 2 points in 3D space do not uniquely define a plane. There are an infinite number of planes that I could draw that contain those 2 points. But as soon as I add a third point, say like this, well, now there's only one unique plane in 3D space that holds those 3 points. The one that I indicated in black would hold those 3 points, for instance. The plane in red would not hold this point here. Okay, so we need 3 points in 3D space to uniquely define a particular plane. Okay, so if we've got that, if we've got some plane in 3D space, we want to find an equation for this plane. And so if we have these, let's say 3 points like this, call it P1, P2, P3, and those 3 points are in that plane, and we can talk about some arbitrary point on the plane, give it the coordinates x, y, z. Okay, P1, P2, P3 are specific points. P is just some arbitrary point. Well, we can ask, we say that P1, P2, and P3 uniquely define this plane, but we want an equation so that we can find any point on that plane. So what can we do? Well, we can draw vectors between these points. A vector like that, a vector like that, and a vector like that. And if we remember from last day, the very last thing we did in our review of vectors was the parallelepiped, which is a three-dimensional parallelogram, if you want to think about it like that, right? Where we said, well, the base of this parallelepiped is going to be defined by 2 vectors. And a third vector is going to define the side of this parallelepiped. I'm not a good drawer, something like this. Okay, this was our parallelepiped. No, that's not right. See, I already screwed up. Let's try that again. Like this. Okay, and I think we call this one B, vector B, we call this one vector C, and we call this one vector A. And we were able to find the volume of that parallelepiped by finding what we call the triple scalar product, which was A dot B cross C, which really just turns out to be the determinant of the matrix, where the vectors A, B, and C are the rows of that matrix. We just find that determinant. Okay, and that gave us the volume of this parallelepiped. Well, we've got for this plane here, we've got three vectors as well, but they're all in the same plane, which would be the same thing as in our parallelepiped here, where A is down here. And if A was down here, what would the volume of our parallelepiped be? It would be 0, right? So all we would have to do is we could define these three vectors. We know the coordinates for P1, P2, and P3. So, and this is just an arbitrary point on the plane with the coordinates x, y, z. We could form these three vectors, put them into here, and set this equal to 0. P1, P2, P1P, and P1, P3. And so we could find that determinant, set it equal to 0, and we'd now have an equation with x, y, and z and some numbers in it. And that could give us the equation for our plane. So that's one way to do it. Unfortunately, it becomes a little bit messy, so it's not a great way to do it. Okay? So we're going to do it a little bit differently. Let me go back here. Okay, so we're still going to make use of this triple scalar product, where we're looking for the determinant of P1P, P1P2, P1P3. Okay, it's still the same three vectors inside of that plane, and all these points are on that plane. So instead of finding the determinant, we're just going to rewrite that as our triple scalar product up here. So that means P1P, that vector, dot P1P2 cross P1P3. Okay, so I just rewrote the determinant as the original triple scalar product. Okay, well let's look at this cross product here. This is the cross product of two vectors. If we go back up here, we're taking the cross product of P1, P2, P1, P2 with the vector P1, P3. So we've got these two vectors, they're on the plane, and we're going to take their cross product. And we know that when we take the cross product of two vectors, we get a third vector. And the direction of that vector is normal to the two vectors that we took the cross product of, right? Using the right-hand rule, if we take P1, P2 cross P1, P3, we're going to get a third vector. It'll actually point down. Let's call that vector n. It's a normal vector. It's normal or perpendicular to the plane. That's what that cross product gives us. So let's call this n. Okay. Well, we still know that this has to equal 0. If those three vectors, these three vectors are all in the same plane, then this has to be equal to 0. So now all we have to say is P1, P dot n hat, or n, pardon me, is equal to 0. Okay? So this is the requirement for those three vectors to be in the same plane. And n is a vector that's normal to the plane. It's the result of the cross product of two of those vectors, p1, p2 with p1, p3. Okay, so that's what we need to do. So let's say that we're going to make this generic now. We're going to forget about the p1, p2, and p3. All we need is we need to solve this equation where we have a vector that is normal to the plane, and we've got a point on the plane. Remember that P1 is a particular point on the plane, and we know what it is. P is just some arbitrary point on the plane, x, y, z. But P1 is a particular point on the plane. So let's assume we know a point on the plane. And in general, we're just going to call that point P0, just to make it general, okay? So there's specific values x naught, y naught, z naught that define this point P0 on the plane. Well, this equation up here tells us that P0P, again, P0 is a particular point on the plane with coordinates x naught, y naught, z naught. P is any other point on the plane with coordinates x, y, z. And n is a vector normal to this plane. But that's got to be equal to 0. Okay, well, we can determine, or we can write mathematically what this vector P naught P is. It would simply be x minus x naught I hat plus y minus y naught j hat plus z minus z naught k hat. Okay. The point P with coordinates x, y, z is the terminal point of that vector. The point P naught with coordinates x naught, y naught, z naught is the initial point of that vector. So you just difference those coordinates and you got the vector going from P0 to P. Okay, so that's what this is. This is P naught P. And let's say that this normal vector n here, let's just give it some values, a I hat plus b j hat plus c k hat. Okay, n is that vector that's normal to the plane. Okay, I've run out of room here, so I'll put dot and then we'll continue down here. A I hat plus b j hat plus c k hat. So we're just taking the dot product of p naught p, which is this, with the vector n, which is this normal vector. And that's got to be equal to 0. Okay, well, if you do that dot product, it's just this, oh, pardon me, I don't want to do that. It's just this times this, plus this times this, plus this times this. Because this is a dot product. The result is a scalar. Okay, so what we end up with is a times x minus x naught, plus b times y minus y naught, plus c times z minus z naught. That's just that dot product, and that's got to be equal to 0. Okay, or I can rewrite that. Ax plus by plus cz is equal to ax naught plus by naught plus cz naught. Or I could write it as ax plus by plus cz is equal to d, where d is all of this. Okay, and this is our plane equation. Okay, that's going to be the equation that defines a particular plane. The particular plane it's defining is the plane that has a vector that is normal to it, and that vector is a I hat plus b j hat plus c k hat, or if you prefer, you can write it this way if you like this better. Same thing. Okay, so there's a b and c are specific numbers, and they give us this normal vector. So the plane that this equation describes has this normal vector, and it has a particular point on the plane, x naught, y naught, z naught. X naught, y naught, and z naught are numbers. They're the coordinates of a particular point on the plane. So this gives us the equation for that particular plane with this point, x naught, y naught, z naught, and this normal vector, ABC. Okay, and that's it. That's our plane equation. So again, ABC for a particular plane will be numbers. This D, which is made up of this, will also be a number. X, Y, Z are our variables. Okay, so this gives us an equation in 3D, X, Y, and Z, that defines a particular plane. Okay? Any questions so far? Okay, so the coefficients of the plane equation and by that I mean A, B, C, those coefficients are the components of a vector normal to the plane. To find the equation of a plane, we need two things. One, we need the coordinates of a point on the plane. And two, we need a vector normal to the plane. Okay, we need x naught, y naught, z naught, and we need this vector a, b, c. If we have those two things, we can write the equation for this plane. If the plane we're trying to write the equation to contains the origin, which means one point on the plane is 0, 0, 0, what does our plane equation become? What would the right-hand side of our plane equation equal? If the plane includes the origin of our coordinate system. Well, it means x naught, y naught, and z naught are 0, right? One particular point on the plane is the origin, 0, 0, 0, which means this would just be 0. Okay? Okay, so to find the equation for a plane, you need a point on the plane, and you need a vector normal to the plane. Conversely, if you have the equation for a plane, you already know two things about the plane. You know a vector that's normal to it, and you know a point that's on it. Okay? Let me ask you this question. If you have a particular plane in space, would the equation for that plane be unique? And the reason I ask that is somebody might ask me, okay, well, if all I need is a point on the plane and a normal that's and a vector normal to the plane, are there not an infinite number of vectors? If I go back to my plane up here, are there not an infinite number of normal vectors that I could draw to this plane? There are. I could draw one like this, I could draw one like this, I could draw one like this, right? Different magnitudes, some pointing up, some pointing down. There's an infinite number of vectors normal to the plane. There's also an infinite number of points on that plane. I've got points all over the place here, right? I can use any one of those points and any one of those normal vectors to describe my plane. So does that give me an infinite number of equations for this plane? And the answer is no. There's one unique equation for each plane, even though you can use an infinite number of normal vectors and an infinite number of points on the plane to write it. And if you want to convince yourself of that, then just take any plane equation and you can find a normal vector to it. It'll just be ABC. Multiply that vector by that normal vector by -3. You'll get another normal vector that'll be 3 times bigger, pointing in the opposite direction. Find a different point on the plane, combine them together, and you'll get the same plane equation. Okay, so there's one unique equation that defines every plane in space, but you can use any normal vector for that plane and any point on that plane to write it. Okay, any questions so far about our plane equation? Okay, let's look at a few examples. So we're given a vector v is equal to 1, 2, -1, okay? And we are given the plane x plus y plus 3z is equal to 5, okay? Very common error that students make at the beginning is they see an equation like this and they assume it's a line in 3D space. You know, because you're used to seeing things like x plus y is equal to 5 being a line in 2D space. Okay, that's a mistake. This is not a line. We're going to look at the equation for a line in 3D space in the next lecture. This is an equation for a plane. There are an infinite number of points x, y, z that will satisfy this equation, indicating that those points sit on this plane. Okay, so we're given this vector and we're given this plane, and we're asked our v and the plane, are they parallel to each other? Perpendicular? Or is their angular relationship something other? Well, how do we tell? Okay, well, we've got some plane, and sometimes, most of the times in this course, it really helps if you sketch it, make a sketch of what's going on. Okay, you don't have to draw it accurately to scale or anything like that. We know we've got some plane, x plus y plus 3z is equal to 5, and we've got some vector in space. I don't know, just draw it in any way. Let's say v looks like that. And this is our plane x plus y plus 3z is equal to 5. Well, how can we tell if v is parallel to that plane or if it's perpendicular? Well, one way we can do it, or really the simplest and easiest way, is because we have the equation for this plane, we right away know that we have a vector normal to the plane, right? Our vector normal to this plane is going to be equal to 1, 1, 3, the coefficients of x, y, and z in our plane equation. So that gives me a vector normal to this plane. So now I got two vectors. I got this vector n and I've got this vector v. And how do we determine whether what the angular relationship between those two is? Well, we've got v is equal to 1, 2, minus 1, and we've got n is equal to 1, 1, 3. Well, are those the same vector, first of all, or is one vector a scaled version of the other? Can I multiply vector v by something to give me vector n? No, I can't, right? So they're not scaled versions of each other. So we know that n, the vector n, and the vector v are not parallel to each other. Well, are they perpendicular to each other? Well, how can we tell that? Well, what if we take the dot product of v and n? And you'll get 1 times 1 is 1, plus 2 times 1 is 2, plus -1 times -3 is -3. I get 0. Right? And remember, the dot product is the magnitude of the one times the magnitude of the other times the cos of the angle between them. Since v and n are not zero vectors, that means the cos of theta is equal to 0. Which means what? Well, that means that theta has to be equal to 90 degrees, which means that v and n are perpendicular to each other. Okay, these two vectors are perpendicular to each other. And since they're perpendicular to each other, and n is perpendicular to the plane, well, that means v must be parallel to the plane. It doesn't have to be in the plane, but it does have to be parallel to the plane. So I should have drawn v maybe like this instead. Okay? So what we did is we basically wrote n from the plane equation. We then looked at the relationship between v and n. We know v and n are not the same vector, so they're not parallel to each other. One's not a scaled version of the other, so they're not parallel. So we took their dot product, found that was 0, and we know that when two vectors have a 0 dot product, they're perpendicular to each other. So v and n are perpendicular to each other, and since n is perpendicular to the plane, well then the plane and v must be parallel to each other. Okay? Any questions on that example? Okay. So this is a favorite problem when it comes to plane equations. Find the shortest distance between a point and a plane. Find the shortest distance from the point S, which has coordinates 1, 1, 3, to the plane 3x plus 2y plus 6z is equal to 6. The point S is not necessarily on this plane. In fact, it isn't on this plane. I find in the past that some students will just try to memorize equations and formulas. And sometimes that works, often it doesn't. It's much better to read the problem, try to visualize what's going on, and then form your strategy from that. Now for this particular problem, in the lecture notes, you'll find that there's two different methods that will show you how you can do this. And for a lot of these problems, there is more than one way you can do it. Just memorizing that, well, I take the projection of one vector and of another, or I take the cross product between two vectors, just trying to memorize equations doesn't work very well, okay? Try to visualize what's going on, and again, if you can sketch it in any way, it helps tremendously. If you can visualize it all in your head, good for you. I don't tend to be that way. I tend to have to draw pictures. So again, we've got a plane, so we'll just draw a plane here, and that's our plane, 3x plus 2y plus 6z is equal to 6. And we've got some point in space S. Okay, let's just draw it up here. That's our point S. And we're trying to find the shortest distance. Well, obviously that's going to be the perpendicular distance, right? That's the distance we're looking for. We're not looking for that distance. That's not going to be the shortest distance. We're looking for the perpendicular distance. Okay, so we've got this plane equation, 3x plus 2y plus 6z is equal to 6. Okay, well right away we know a vector normal to this plane. We can write it just from the plane equation, right? It's just the coefficients of x, y, and z in the plane equation. 3, 2, 6. Right? 3, 2, 6 give us our vector that's normal to the plane. Okay, and I'm gonna, I don't know, maybe draw that vector like that. There's a vector normal to the plane. My vector 3, 2, 6. Okay, well from the plane equation, we can get any point on the plane as well. Right? All we have to do to find a point on the plane is find an x, y, and z that satisfy this plane equation. Any combination of x, y, and z that satisfies this plane equation will be a point on the plane. That's what it means to be the plane equation. Oh. Sorry, go ahead. Question? No? Okay. Okay, so I can find any point on this plane simply by substituting values of x, y, and z in here that will satisfy this equation. Well, for instance, I could say, well, what about this point? 0, 3, 0. An x value of 0, a y value of 3, and a z value of 0. Will that satisfy this plane equation? Yes, it will, because 0 plus 2 times 3 plus 0, 6 is equal to 6. Right? So this is a point on the plane. What's another point on the plane? Well, how about 2, 0, 0? Would that point also satisfy that plane equation? Yeah, 3 times 2 plus 0 plus 0, 6 is equal to 6, right? So I could choose any point on this plane. Okay, I'm just going to choose the first one here. Doesn't matter which one I choose, 0, 3, 0. And let's say that I'm going to put that guy right there, where my normal vector is. 0, 3, 0. This is a point on the plane. Okay, so I've got a point on the plane. I've got this point in space S, which is 1, 1, 3, we're told. I can draw a vector from P to S. And I can calculate what that vector is, because I know the coordinates of where it starts and where it ends. Okay, so PS is simply going to be equal to 1, 1, 3, which are the coordinates of S, minus 0, 3, 0, which are the coordinates that I chose on the plane, which are P. That gives me 1, negative 2, 3. Okay, so that's my vector PS. Okay, well, I can move this n vector anywhere. As long as I don't change its magnitude or its direction, I can put it anywhere. So I can move it over, say put it over here. Okay? And I'm interested in finding this distance here. Well, that distance is going to be the projection of this vector PS onto this direction, onto this line, which is defined by n. So all I have to do is find the projection of this vector, which if I put a light over here shining in this direction, casts a shadow on this line, the length of that shadow is going to be the distance d that I'm looking for. So all I have to do is find the projection of this vector PS onto the vector n, because n is on this line. So d is simply going to be the absolute value of the projection of PS dot n hat. That gives me the projection. Okay, and technically let's just leave it at that. Okay, so this is where I said knowing how to find the projection of one vector onto another one is very handy. In this case, it gives us the distance that we're looking for. Okay, well this is n hat, which is a unit vector. When we find the projection, the second vector, the vector that you're finding the projection onto, has to be a unit vector. Okay, n here is, where is it? N here is not a unit vector. This vector does not have a magnitude of 1. Its magnitude, its length, is much bigger than 1. Okay, so that means we have to normalize it. We have to divide it by its magnitude to turn it into a unit vector. Sorry, I should have written PS here. PS dot n hat, and n hat is just n divided by its magnitude. That turns it into n hat. And the magnitude of n is 3 squared plus 2 squared plus 6 squared. That's 9 plus 4 plus 36. That's 49. Take the square root is 7. So you divide it by 7. So we get 3 over 7, 2 over 7, 6 over 7 is our n hat. And you do that dot product, 1 times 3/7 plus -2 times 2/7 plus 3 times 6/7, and we end up with 17/7. So that's the distance we're looking for. All right, any questions about that example? Okay, if you have a question, either raise your Zoom hand or just speak out, okay? I'm not checking the chat box because I can't do that at the same time as lecturing. So if you have a question, just speak out or raise your Zoom hand. Okay, so that's method one. That's one way we could do this. Using the projection of our vector PS onto the normal vector n. We get the normal vector n from the plane equation. We get the point P on the plane just from the plane equation. We already are given point S. So we can form PS, we've got n, we do the projection, we got the distance. Okay, let's look at a second method. So let's draw our plane again. And we've got a vector that's normal to it. We can just write it right from the plane equation. We've got this point S that we're given. Okay, and we're looking for this distance. Okay, that's the perpendicular to the plane. Well, let's say this point on the plane, which is right below S, which is on the line that connects S to the plane, the shortest distance, let's call it P. And it's got some unknown coordinates x, y, z. Okay, we don't know what x, y, z are yet. That's what we got to find. But if we take this point P and we form the vector PS again, we got this vector PS. Well, what's the relationship between PS and our normal vector n? Well, both of them are normal to the plane, right? Which means that they're parallel to each other. Now, n might look this way. Whoops. N might look like this. It might be pointing down and be normal. We don't know. And it doesn't really matter. We know that PS is parallel to n, whether n is going up or n is going down. And whether PS is going up or PS is going down, doesn't matter. They're parallel to each other. They might be pointing in opposite directions. They might be pointing in the same direction, but they're parallel to each other. Which means that we can write PS is equal to some scaled version of n, where k is some scalar value. It might be a positive number, in which case PS and n are pointing in the same direction. It might be a negative number, in which case they're pointing in opposite directions. If k is equal to 1, well then PS and n are the same vector. They have the same magnitude. If k is equal to -2, well then they point in opposite directions, and PS has twice the magnitude of n. Okay? But in any case, they're parallel. It doesn't matter what value of k we use, positive or negative, big or small, this equation says PS and n are parallel, and we know that that is the case. Okay? We're setting it up that way because we want to find x, y, z for this point then. Because once we find x, y, z for this point, well, we've got 2 points in space, we can surely find the distance between them. Okay? So we say, okay, I'm going to make this point P to be directly below S on the plane so that this equation has to be true. Okay, well, we can now write PS. PS is going to be what? PS is going to be 1 minus x, 1 minus y, because S is equal to what again? S is equal to, I should write that down, 113. 3 minus z is equal to k, and what is n? N was, if we go back, oh, pardon me, nope. We go back here, n was 326. Okay, which means 1 minus x is equal to 3k, 1 minus y is equal to 2k, and 3 minus z is equal to 6k. For those two vectors to be equal, their respective components must be equal. So 1 minus x equals 3k, etc. Okay, we're going to see in the next lecture that this is actually the equation of a line in 3D space. Okay, but that's next lecture. It's the equation of this line here, the line that goes through S and the plane. But in any case, that's for next day, okay? Okay, so I'm going to rewrite this so that x is by itself. So x is equal to 1 minus 3k. Z is equal, y. Y is equal to 1 minus 2k. I'm just rewriting those equations to put x, y, and z by themselves. 3 minus 6k. And remember that x, y, z here are the equations of this point on the plane. Okay? They're equal to these values. Okay, well the point P is on the plane. And remember the plane has the equation, what was it here? 3x plus 2y plus 6z. 3x plus 2y plus 6z is equal to 6. Yeah. Okay. Point P, which has these coordinates, x, y, z, is on this plane. And we've found here that because of this relationship we set up, x, y, and z have these values. Which means if I substitute these values into the plane equation, they have to satisfy the plane equation because x, y, z are the points of this point, which are the coordinates of this point, which I define to be on the plane. Therefore, I just plug 3x plus 2y plus 6z is my plane equation, is equal to 6. And I just substitute 1 minus 3k for x, plus 2 times 1 minus 2k for y, plus 6 times 3 minus 6k for z is equal to 6. Okay, so I just plug these values for x, y, and z into my plane equation. I get that. So I got one equation, one unknown. I just solve for k. I'll find that k is equal to 17 over 49. Okay, and k was this value up here, which gives me a value for PS. PS is equal to k times n, and I know n from the plane equation. I now know k. I just multiply the two together and I get PS. Okay, and the distance I'm looking for, if I go back all the way to my picture here, the distance I'm looking for is the length of this vector PS. So now all I have to do is find the magnitude of PS. And when you do that, you get 17 over 7, which is the same as we got with method 1, right? Yep, 17 over 7. Okay, any questions about that example? Okay, so basically we teach you these simple tools of, a dot product, a cross product, projection, the basic operations having to do with vectors. You now know the plane equation, okay, which is ax plus by plus cz is equal to d. Okay, and knowing all these things, we come up with problems to see if you can use these tools together, right? Magnitude of vectors, dot product, cross product, projection, and really the hard part is setting it up, visualizing what's going on, and then being able to see, well, okay, I know what n is, I know what s is. Well, I can make up a p here on the line, call it p on the plane, call it x, y, z. ps is parallel to n, that means this is true. Solve for x, y, and z in terms of k, and then put those values for those expressions of k that correspond to x, y, z. Since x, y, z is on the plane, then those expressions of k have to satisfy the plane equation. Pop them in the plane equation, solve for k, and now I can find what ps is. It's k times n, and the magnitude of ps is my distance. Okay, so there's usually more than one way to solve these problems, but they all involve vector operations and these simple tools we're giving you. Okay. All right. Any questions about that example? Oops. I'll go all the way to the top. Okay. If not, let's look at one more quick example, and we'll be done for today. Find the angle between two planes. Say plane 1 is 3x minus 6y minus 2z is equal to 15. And the second plane we're given P2 is 2x plus y minus 2z is equal to 5. Okay, so we've got two planes in three-dimensional space, and we want to know what the angle between them is. Well, how are we going to do that? Well, what do we know from the plane equations? We know a point on the plane as well as a vector that's normal to each plane. Well, can we find the angle between two vectors? Yes, we can. We've got the dot product and the cross product that allow us to find theta, the angle between two vectors. So if we can find the angle between the two normal vectors, does that give us the angle between the vectors, or between the planes of those normal vectors? Yes, it does. So we simply have to write down the normal vector for plane 1. It's just the coefficient of x, y, and z. 3, minus 6, minus 2. For plane 2, the coefficients are 2, 1, negative 2. It's that easy. Nothing magical about it. Okay, and we could use, for instance, the dot product, which tells us that n1 dot n2 is equal to the magnitude of n1 times the magnitude of n2 times the cos of the angle between them. And that's what we're trying to find. So theta is the inverse cos of n1 dot n2 over magnitude of n1 times the magnitude of n2. So n1 dot n2 is going to be 3 times 2 is 6. 6 plus negative 6 times 1 is negative 6 plus negative 2 times negative 2 is positive 4. Over magnitude of n1 times the magnitude of n2. So magnitude of n1 is going to be 9 plus 36 plus 4, which is 49 square root is equal to 7. Magnitude of n2 is going to be equal to the square root of 4 plus 1 plus 4, which is 3. 3 times 7 is 21. So we're going to get 1.38 radians. Okay, so that gives us the angle between the two normal vectors, which is obviously also the angle between the two planes. All right, so in summary then, if we're on a quiz or on the final exam, what are the type of questions we can ask with regards to planes? Well, We can ask you to find the distance from a point in 3D space to a plane. That was our first example. We can ask you to find the angle between the two planes, which we just did. We could ask you to find the plane equation that corresponds to a point in a normal vector. That's pretty easy. You can just write it down. We can ask you to find the equation for a plane if we give you a point and another plane that's parallel to the first plane. Or if we give you 3 points, what's the equation of the plane that those 3 points are on? If we give you a point and a line that is perpendicular to the plane, could you write the plane equation? And given a point and a line that the plane goes through, where the point is not on that line. Okay, these are all examples. You can see them at the end of the lecture notes on page 5. And I encourage you to take a look at those and just think, well, what would your strategy be? What would you do to find the plane equation of a plane if we give you 3 points on the plane? Obviously, you're going to create some vectors. Maybe take a cross product. Now you got a vector that's perpendicular to the plane. Okay, so we're done for today. Any questions? I'll stay online for a minute or two. Otherwise, we'll see you Wednesday. Perhaps in person, perhaps on Zoom. Look for an email again. Thank you, everyone.